Hello, this is Tom from anti-proton.com, and this is part 2 of radiation and how much radiation is dangerous for you. We talked about alpha particles. Those are just helium nuclei, just 2 protons, 2 neutrons. They're very positively charged, and they tug at everything when they go by, and they only go for a short distance. That's why they're dangerous. Then we talked about beta particles, and we said that they are electrons. Energetic electrons. Now, in reality, they can also be the anti-electrons called a positron. You can have them too, and they're very positively charged. But you kind of sort of maybe get the point of what's going on now. You have these particles that are positive or negatively charged, and they're flying away from these really out of sync atoms. These atoms that are radioactive that have to release this energy so they can calm down and relax. So they're shooting this stuff off every direction. So these alpha and beta particles are causing untold amounts of damage as they hit you. Alpha only goes a couple inches, but beta can go 10, 15 feet sometimes. Usually it only goes a couple of feet, depending on how powerful it is, how much energy it has. All right? Potassium in your banana, potassium in your light salt, that's producing beta. It's not very damaging to you, even though you're ingesting it. Now, if you were to crush it into powder and breathe it, that might not be the smartest idea, but still not too much damage overall. Beta does the next amount of damage to you, the next most amount past alpha. The third to think about is gamma. Gamma is a photon, just like light from the sun. But it's at a very high frequency. And with light, the higher the frequency, the higher the frequency, the shorter the wavelength. Squeeze the wavelength. Light's always going the same speed, so as you squeeze the wavelength together, making it shorter, it must be going past you more frequently. And thus has more energy to do that. Squeeze and it need more energy. So if you took a photon coming out of your light bulb, and you could somehow magically grab it and make it much squeezed up, much more tiny wavelength, it would become dangerous to you. Of course, a light won't, but that same block of uranium that's producing the alpha we talked about earlier that you're stopping with your sheet of paper because you're so cool, unfortunately, it's also blasting you every now and then with gamma particles. Oh, not particles, but gamma waves. They're sort of particles and waves. Remember particle-wave duality if you want to get physics about it? But anyhow, the gamma radiation is not as deadly, believe it or not. Yes, I know it made the Incredible Hulk, etc., but not really. But gamma radiation flies right through you. Because of the crazy funkiness of quantum mechanics, if it can't deliver all of its energy to you, then it can't deliver any of its energy to you. It'll fly right through you. Most of the time it stops. Like if you hold a glass bottle up and most of the light goes through it, that's why. Now, gamma rays, most of them will pass through you, kind of like X-rays, but some of them will stop, and the ones that do stop because they hit your atoms will impart a humongous amount of energy. They'll blow electrons off and all kinds of crazy stuff. That's why they can be deadly, but they're not as deadly as alpha. The problem is you can't stop them. If I put a couple of bricks up, I can stop alpha and beta. But I need a few, maybe an inch of lead to stop gamma. That's why gamma can in its own way be a little more dangerous sometimes. Anyway, X-rays are basically the same idea as gamma. They're just not as powerful. They're like a lower power. If you take a gamma ray and you make it less and less powerful, it would fall into the range of X-rays eventually. They go right through you, and that's why they're so good for medicine, because they can fly right through you and be red on the other side, but some of them get stopped, and the difference between going through you and not going through you is how you see whether there are bones or not. That's how an X-ray machine works. Very simple, actually, when you really think about it. If you took a barrel and you put a block of steel in it and then you shot a machine gun, on the wall behind the barrel, you'd see where the wood parts got penetrated by the bullets, but the center part where the block of metal was, there wouldn't be very many bullets at all. And that's how you would know there was a block of metal inside the barrel you just shot up. So, I'll give you an analogy. So that's alpha, which is a particle. That's beta, which is a particle. That's gamma and X-ray, which are both waves of effectively light, if you like. They're in the electromagnetic spectrum. The last thing is neutrons, and a neutron is a specific particle. It's actually technically made of 3 tiny little particles called quarks, but forget that for a second. It's a neutrally charged particle, brain lock. And that means it isn't positive or negative. It doesn't affect anything when it hits, it just goes right past, but it's so heavy, so much mass to it, that when it slams into stuff, it's like a cue ball, just knocks stuff all over the place. Like a bowling ball, more likely. And the other problem with neutrons is that they can be absorbed into atoms and cause some atoms to undergo fission, where they split, or cause something called secondary ionization, where an atom technically can become radioactive that was not already radioactive. So that's like the lowdown, the skinny on radiation. All right? Uranium produces alpha, and occasional gamma. Your light salt produces beta, as well as positrons, which is positive beta. Fission produces gamma and neutrons. Cesium-137, you keep hearing about in the news, that produces gamma. Iodine, I think off the top of my head, iodine-131, you keep hearing about that in the news too. I believe that's a beta emitter. And I can't remember what strontium-90 puts off. That's the other big one in the news. Off the top of my head, I think strontium is a beta and gamma emitter. That's off the top of my head, though, so you might want to look that one up. The other ones I'm sure of. That one I'm a little iffy on. Now, let's talk about what's safe. I'm being bombarded right now by cosmic radiation, coming down from the sun and the stars, etc. Perfectly normal. I'm about at sea level, give or take. So if I had a little tube of gas that could detect radiation, we'll call it a Geiger tube, this little tube of gas, about the size of, let's say, a AA battery. We'll fill it with gas and we'll charge the outside of it with a lot of energy. We'll call it, let's say, a lot of positive electricity. Then we'll put a wire in the middle of it, and we'll be sitting there waiting for it to connect. If electricity can flow from the outer casing through the gas to the inner tube, then you'll get a circuit completed. Make sense? Positive, negative, and here are the two together. And in between here, in between, see, I can't do it very easily. Here, let's try this. Positive, negative, and see in between my two fingers? You need a circuit to connect. You need electricity to flow between the two. To make that happen, there's gas in between. If radiation flies through that gas, it will ionize it. Remember the positive and the negative, and allow a little tiny drop of energy to fly by, just enough to complete the circuit, and you get a tick. There's your famous Geiger counter tick. That's where it comes from. Tick, 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 tick. The bigger the Geiger tube, the more ticks it gets. The Geiger tube on most Geiger counters is a little over an inch long, inch and a half, give or take. And it's full of a halogen gas. It can be various things, including chlorine, all kinds of random things. And they usually have a lot of voltage, but very little amperage. And what happens is when the radiation goes through, alpha, beta, gamma, X-ray, it makes the click, a tick, a count. If you got one tick, give or take about every second, then that would be, what, 60 counts in a minute, right? 60 times a minute, once a second. If it happened twice as fast as that, it would be 120 counts per minute, wouldn't it? Because that's how many counts, that's how many tick, 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 tick you got. Radiation tick, tick, ticks up and down all the time. A little bit more, a little bit less. So you do an average. And most Geiger counters kind of do a running average. They take into account how long they have, like a sliding window kind of, and they use that to average. So you're hearing the ticks, that's every time it gets hit. But on the dial or the digital reader, you're usually getting an approximate average of what it would be given time. That's counts per minute. Right now, I know that I'm being exposed to, because I've checked this area, about 14 to 16 counts per minute, every minute, for a little tiny area about the size of an inch and a half. If I were to calculate for my whole body, technically speaking, it could be several thousand counts per minute. So when you read a Geiger counter, you're actually looking at a very small, little tiny bit of area, very small amount. And that can be a problem with people, because they go to the store and they buy a Geiger counter that has a really big, wide, these big circular things called pancake Geiger-Müller tubes. Big circular ones. And they'll pull it out of the box, and then they'll run outside and say, wait a minute, everybody else is saying that they're getting 20 counts per minute, but I'm getting 60. There must be radiation. Well, of course there's radiation. There's radiation everywhere. But the pancake is 3 times bigger, so it's reading 3 times more. Just because it's bigger, more chances for stuff to go through it. It doesn't actually hurt anything. And it doesn't mean that there's anything bad going on. For part 3, I'll tell you a little bit more about Geiger counters and what a safe dose is. Yeah, I'm getting there. Part 3 should have it in there. So this is Tom from anti-proton.com. Watch part 1 and part 3 as well.